This lecture is about the history of artificial intelligence. Artificial intelligence has become a major topic of public interest over the last few years. People probably have a sense that work goes back earlier, but may not know that the term goes all the way back to a conference at Dartmouth University in 1956. However, the basic idea of automated procedures to solve problems goes back for thousands of years. The Persian mathematician Muhammad al-Khwarizmi, who was working in Baghdad in the 9th century AD, wrote a book where he compiled all the procedures that the Greek, Egyptian, and Babylonian mathematicians had used to solve various problems. And he showed how to simplify their processes using the new numbering system that people in India had come up with. When the book was translated into Latin, it was so influential in Europe that the translation of his name, algorithmi, became the term for any procedure that could be used to solve a problem. His book also gave the term algebra. Several hundred years later, in the 1600s, the German mathematician and philosopher Gottfried Leibniz, who, along with Newton, invented calculus, which was itself a series of algorithms for solving problems about rates of change and areas, Leibniz proposed the idea that there could be universal algorithms to solve all problems. He was committed to the idea that God had reasons for everything that he did, and with our reason, we should be able to figure out what God's reasons were. If we figured out the right language to express our problems, then we could figure out the right procedure to calculate, and we should be able to solve not just mathematical disputes, but also philosophical ones. This idea remained just a dream of the philosophers for a few hundred years, but in the late 19th century, the German mathematician Gottlob Frege figured out how to design a precise and unambiguous language to express all of mathematics. Here you can see some of the original notation, but if you ever take a class in symbolic logic, you'll encounter the more modern notation of Frege's universal concept writing. Over the next few decades, philosophers and scientists figured out how to express much of their theories in this precise language and thought that this might result in Leibniz's universal algorithm. However, in 1930, the Austrian mathematician Kurt Gödel showed that it couldn't. Effectively, what Gödel showed is that he showed how to translate any statement about any algorithm into a statement about numbers. And then he wrote down a mathematical sentence for any given algorithm that says, your algorithm can't solve this problem. And the idea is that if your algorithm could solve the problem, then your algorithm would be getting something wrong. And if it couldn't, then there was a true sentence that your algorithm couldn't get. Either way, no algorithm could properly be universal, solve every problem correctly. However, in 1936, the British mathematician Alan Turing was able to turn this into something more productive. Although no algorithm solved every problem together, he showed that there still is a universal algorithm that can solve any problem that has an algorithm at all. That is, what he devised was a universal coding system in which you could encode the instructions for any algorithm, and then his universal algorithm would implement it. In 1936, the idea of Alan Turing's universal algorithm was still theoretical. It was just a mathematical idea that he had, though he had the instructions for how to translate it to a specific kind of machine. During the Second World War, the British intelligence agencies realized that they needed advanced methods to break the German codes, so they hired Alan Turing, along with many others, to come to their secret center where they were running their code-breaking operations. During the war, they actually built a lot of machines that implemented some of his algorithms, and with great success, they probably enabled an earlier victory in the war than there would have been without this machine. After the war, Turing started working at the University of Manchester, where he was building more of these universal algorithm machines, or computers, as we call them now. As he was experimenting with writing up the codes for more and more algorithms to run on these machines, he gradually got an understanding of the true power of algorithms in a way that no one ever had before. Although there are classes of problems that no algorithm can solve, as Gödel showed, there is a wide range of things that algorithms can solve. And even though the instructions have to be specified in advance, it turns out to often be extremely difficult to predict what an algorithm will do until you just run it. And as a result, in 1950, Alan Turing published a very influential paper, Computing Machinery and Intelligence. In this paper, he proposed that within a few decades, it would be natural to say that computers can think. Since we can never get into anyone else's head to know what they are thinking, he suggested that the test for figuring out whether or not a machine is thinking should be the same as the test that we have for figuring out whether or not a person is thinking. See if you can have a conversation with them and see if that conversation is interesting enough to keep coming back for more conversation and treat them like a friend. And so he says, if you can have that sort of extended conversation with a machine, that's all that matters, regardless of whether the machine is running on punch cards and vacuum tubes or brain cells and blood. As long as it's doing things that we can't predict in a way that keeps us coming back, that's the real test of intelligence. Now, Turing didn't himself propose what this algorithm would look like that might be able to imitate intelligence in this way. But one idea that he proposed, which has been highly influential, is the idea that rather than trying to program a computer to have conversations like a human adult, it might be easier to program the computer to learn and then raise the computer like a child and let this learning result in meaningful conversations. About a year after publishing this paper, Alan Turing's house was burgled, and he told the police that the burglary was committed by a man that he had recently started dating. However, rather than track the burglar down, the police arrested Alan Turing because at that point, homosexuality was illegal in England. He wasn't sent to jail, but he was forced to take medication that suppressed his sexuality, and a few months later, he committed suicide. However, his ideas were out there. Researchers in the United States soon started building computers of their own, and some of them started trying to figure out how to design algorithms that could reason about the world, interpret images from cameras, control robot bodies, and do various other things that might be components of intelligence. And in 1956, the mathematician John McCarthy, who was working at Dartmouth University, gathered several dozen of these people together at a major summer research project, and he coined the term artificial intelligence for the projects that they were working on and making progress on. Over the next decade or so, there was a lot of progress in these things. The invention of the transistor allowed computers to start getting smaller and more powerful, as Turing had already been predicting. Algorithms were being written that could play checkers and could prove simple mathematical results. Another major breakthrough at this time was that neuroscientists had figured out that the brain was made out of mostly a single type of cell called a neuron. And they realized that the firing of a neuron was almost entirely controlled by the firing of the neurons that feed into it. Since this is how the brain works, many people started thinking maybe we could build machines like this instead of building machines to follow instructions like Turing suggested. And so in 1957, Frank Rosenblatt showed how to build a network out of neurons that could be used to identify shapes in front of a camera. And these neural networks became the core of a competing paradigm for artificial intelligence that relied more on learning and training than on people designing an algorithm. But in the next few years, there was more progress, but the hype started getting out of control. There were early robots being introduced into factories and perhaps doing other things. In 1964, the computer scientist Joseph Weizenbaum at MIT wrote a very simple program called ELIZA, which pretended to be a psychotherapist. But all it really did was just take whatever you said, turn it back into a question and ask you. However, some people got really into this. They thought that it was a real therapist that was understanding them, even though the program was remarkably simple. The US military started funding projects to try to do automatic translation between Russian and English, but they soon discovered that translation was a much harder problem than they thought. Just going word by word wasn't going to work. As they say, the sentence, the spirit is willing, but the flesh is weak, turned into the vodka is good, but the meat is rotten. So they needed to somehow get more knowledge into there. In 1966, the researcher Marvin Minsky at MIT decided that some of his students would just be able to solve the problem of computer vision that summer. And although his project failed, and computers still can't even do all the things that humans do with vision nearly 60 years later, Minsky then predicted that human intelligence level was just a few years away. When this didn't materialize, in the early 1970s, a lot of research programs were cut. The British government cut most of their funding. Many researchers in computer science left AI for other areas of computer science that were starting to develop around then. And this period in the 1970s came to be known as the first AI winter. However, a few years later, around 1980, things started picking up again. This time, there was more of an emphasis on business applications rather than the theoretical general problems of intelligence. Automated reasoning systems were designed that corporations were starting to actually use to help with their business processes. There were new methods of training neural nets that were developed that enabled the automated the automated computer recognition of handwritten zip codes on packages for the postal service. Some of the first toys that incorporated robotic elements and robotic voices were built, like Teddy Ruxpin. But in 1987, there was another bust, and the second AI winter began. The symbolic reasoning systems that had been showing promise in the early 1980s were reaching their limits. It became clear that they depended on too much human labor to input the information that they would reason with. And perhaps more importantly, around this same time, the invention of the World Wide Web and the mass availability of email to the general public started attracting computer scientists to the internet rather than to AI. However, throughout the 90s, there were researchers working on AI, and more progress started being made by the end of the decade. By 1997, increased computational power allowed Deep Blue, a computer that just looks ahead a large number of moves, to beat Garry Kasparov, who was then the world champion of chess. Over the next few years, many important developments that might now be seen as AI came without using that term. In 1998, Google started providing a more informative way to find websites based on keywords. Rather than just returning the site with the most uses of a word, they had a way of categorizing the most authoritative sites. In the early 2000s, advertisers began to more intelligently target their ads. Mapping sites began giving people useful route information, and the first autonomous vehicles started operating on Mars. Years later, by around 2010, it became clear that the increase in computing power, and especially the specialized computer chips that had been designed for computer graphics, were actually really useful for running neural nets of the type that had been invented in the 50s and started being useful in the 1980s. And soon, neural net-based systems started outperforming many of the other systems. There was a sudden acceleration in fields like computer vision, with a system AlexNet that was able to identify images of thousands of different types. Uh, and then these were able to be used for autonomous vehicles like this early car from Google. And researchers started figuring out how to start back engineering these neural networks to use them to create images like this Deep Dream system from the mid-2010s. We still don't have computers as generally intelligent as the ones that Alan Turing had envisioned in 1950. But his basic insight that it would be easier to design algorithms for learning than to write the algorithms of intelligence ourselves was importantly right. Much of the important conceptual work for artificial intelligence was done decades before there were any machines capable of running these ideas, particularly when it comes to neural nets. On a few occasions, the hype has gotten ahead of the reality, and there have been some AI winters. It's always possible that there could be another AI winter, or it's possible that AI has now crossed a threshold and will, from now on, always be a central feature of society.